if I substitute into this relation, I will get this H. Okay, so these are all relations basically. And if the problem statement is given the dimension of the conductor, how I can solve this problem? It is nothing but extension of this relation. Suppose if I take a conductor, the thickness is given as a T and length of the conductor is given as L, and what is the area of the conductor? So for example, this is a conductor extending behind and front. Okay, so what is the area of the electron which is flowing across this area? Is nothing but current density J. So J, I can write the current divided by area. So area is nothing but length of the conductor, or you can take width. It's look like a width, so let's take this is W, the width of the conductor times of thickness. That will give me the area. So I will substitute this current density, the relations to the Hall field. So EH I can write as minus I times of magnetic field divided by W times of T. This is nothing but area times of N into E. So some problems they will give the dimensions, they will ask to find out Hall field. So once I know the Hall field, if they ask what is the Hall voltage, so it is nothing but what is the Hall voltage you are measuring across this conductor. So this is basically to the apply voltage that you are getting the electric field. This is across the conductor in other directions is nothing but Hall voltage. That is due to the distance. Here the distance is nothing but, we have to keep it in mind. So always we know that electric field is nothing but voltage divided by distance across the voltage in the 2 points. If I take these two distance, the potential difference between these 2 points is V. If the length of the distance between these 2 points is L, so that will give me the electric field. So what is the distance between these 2 points? Is nothing but width, mentioned as width. So here if problem is given is Hall voltage, I can write VH is nothing but the distance across this 2 point W times of electric field. If I rechange this equation, can be written as the Hall voltage also can be written as minus I times of B times of N into E times of T. So W and W will be cancelled out. So this is also one of the relations. It will be quite useful in the problems. And how now we have seen that electrons, how it is generating the force, Lorentz force in the conductor. Quickly we can see that how the holes is generating the force. If I take the holes as a reference, where is the force will be. So I can take another picture, give them more clarity. So if I take this picture, if I take, this is a holes carrying the velocity Vd, this direction from left to right, and this is my index finger in the right hand principle, and if I take cross magnetic field, the magnetic field is a middle finger, it's going inside, so the force is going inside, we will take it as always cross. I think you know that magnetic field inside, so back of the arrow will be cross, and where will be the product of it's a cross product of these two is nothing but force acting on this holes. It is in the top one, so that holes is forced to the going to the top, so electron will be naturally become the bottom. So if we take the multimeter and measure this, now the conventional current direction is this side, so the reading will go in one direction. Okay, this will give me the current, and through that I'll find out the voltage. So it will give one direction if it is holes, and if it is a electron is carrying current, it will give the another direction. I'll take another color. So if it is an electron, it will be the other direction. So from this I can make out which carrier is carrying the current. So this is simple rule, right hand principle, have to little more clear, and you can see that the electric field always from positive to the negative. This is electric field. So from the due to the Hall effect, what is the Hall field is opposing the Lorentz force. So we quickly go to the problem. We'll take one of simple problems to solve this. Okay, let's say the strip of the copper 150 micrometer thickness is placed in the magnetic field of the value 0.65 Tesla. So unit for magnetic field is nothing but Tesla, and perpendicular to the plane of the strip, and the current I is 23 amps is set up in the strip. What all potential difference V would appear across the width of the strips if there were one charge carrier per atoms? If I assume that one whole charge of the carrier, so all the atoms is carrying one charge, so total number of the electrons is nothing but n. If each electron is carrying the charge Ne, so I can apply this Ne in the relations to find out the Hall potential. If I recollect the equations, I know that VH Hall field is nothing but J times of B divided by minus Ne. Okay, minus Ne times, if I just recollect it, minus Ne times of B minus J, or here I can put plus, so minus JB over Ne. This is my Hall potential. This also can be written with a dimension. This can be written as we mentioned earlier, this is current divided by area. So area, if you take for the conductor, as I discussed already, this is my thickness is given as 150 micrometer. This is my width of the conductor is W. So if I take a area, it's W into T. So current density is nothing but current over area. So this is minus I divided by area is W into T into N into E. This is magnetic field is that minus IB is multiply with W. It's not it, because EH I will have this formula. Just small corrections here. This is VH is nothing but there is a W will come here, because EH is nothing but VH over W. Distance between these two, VH is nothing but EH times of W. So this is my EH, this is my W. So EH time of W, this is the Hall field. So in this problem, what is given? So here T is given 150 micrometer and B is given 0.65 Tesla, and current is given 23 amps. So which will be a correct formula to use this? The Hall field equals to, so this will be give the right formula for me. This is minus I into B divided by N number of electrons and charge of electrons into thickness of the conductor. So this W and this W will be cancelled out. If I substitute all the value, 23 into 0.65 Tesla divided by number of electrons. What is the number of electrons? It's not given in the problem, but since it's mentioned copper have a FCC structure, and we take all valence electrons valence electrons equals to free electrons. So we can find this value from the previous one of the problem mentioned in the textbook. Since it's F3 structure, so it have a atomic density of, if it is lattice constant, for example, if I take lattice constant is, for example, it is given as in the previous problem, it is nothing but A, it is 0.360 nanometer. This is my lattice constant between the atom. If it is F3 structure, I'll have a front of atoms and back side and right, left, top, bottom and corner atoms. If I add everything, I'll get total atoms is 4 per unit cell. Okay, for more idea to see the previous problem mentioned in the Drudge theory. So here, so 4 atoms per unit cell and total number of volume is nothing but AQ times of, I take one copper will have one valence electron, so it is nothing but free electron. So if I substitute A value is 0.36 nanometer, that whole cube, I will get N is nothing but around 8.6 into 10 to the power of 28 atoms per meter cube. So I got n value. So in these equations I can substitute n value 8.6 10 to the power of 28 into, this is charge 1.6 into 10 to the power of minus 19 into T thickness is 150 into 10 to the power of minus 6. If you substitute all the values, I will get 7.24 into 10 to the power of minus 6 voltage. This is voltage. Even if it is put negative, only the polarity changes. So the absolute voltage, it is 7.24 into 10 to the power of minus 6 voltage. Microvolt, 7.24 microvolt. So this is a problem. We can solve similar kind of problems, and this is all about problems in the Hall field experiments. Thank you for listening.